Good afternoon, ladies and gentlemen. My name is Roger Took and I represent the naval business of Rolls-Royce. Today I'm going to look at really give you some observations and comments upon modern naval propulsion. Modern naval propulsion today has to be affordable, flexible and extremely power dense. I'm just looking at some of the trends and making some comments on what we're seeing developing in the world.
Yeah, I'll do this way.
Just to quickly give you some idea, the Marine division of Rolls-Royce, of which naval is a part, has two other sectors, the merchant sector and the offshore. The point I want to make here is we actually develop technologies across the sectors. So we actually pull through technology, quite a lot of technology, into naval from offshore these days. And the other point I would make on this particular slide is the three divisions that look at the ships. That's about half of the business. Supporting equipment and systems in ships is half of our business. If we look at a modern combatant, frigate, escort, or destroyer, whatever you want to call it, the sort of range of equipment that Rolls-Royce offers can be seen in this slide. But of course we offer it as systems, as properly integrated systems. So in this particular example we're probably looking at something of a cod log or cod lag system, with the gas turbines, the diesel generators, motors, etc., propeller shafting, and all the other things. The other thing I would note here is in very modern warships, and I'm thinking particularly of the new frigates for the Royal Navy, mission bays and handling mission systems inside a mission bay, including unmanned and manned boats, containers that can take anything or store anything, including additional mission systems. Moving them around at sea under power, unloading them and loading them from the ship is all possible with new mission systems, new launch and recovery systems. Now, if we think about what are the constraints upon propulsion systems in a modern era? Well, first of all, I think we've all seen there are new threats developing, Horn of Africa, piracy, asymmetrical threats, etc., call what you will. But actually they put a different type of constraint upon the propulsion system. You're going to have to stay out at sea for long periods, so endurance must be high, and then if something is detected, very rapid speeds very quickly. We're also looking at frigates and destroyers being multi-role these days. Having a specialist frigate, a specialist anti-submarine frigate, a specialist AAW frigate, anti-air warfare frigate, is probably not going to happen in the future. So that all the vessels are going to have the ability to flex their profile, to change the way they operate. And that requires a very flexible power and propulsion system. Things that actually affect the power and propulsion system can also affect the whole of the platform. But what I'm showing here is operations in colder weathers, getting towards the poles. And really I'm talking about both North and South Pole. But actually, we're moving as well into hotter temperatures. Many navies are experiencing much higher temperatures than their ships were designed for, through operating in the Persian Gulf and places like that. So, the requirements upon the power and propulsion system, and indeed the platform itself, means it must go from extremes of cold to extremes of heat. And we have to design that at the very beginning. Legislation is also affecting the way we use power and propulsion. Certainly the legislation regarding emissions, both CO2 and NOx, etc., affect what you're actually having to put on ships and driving diesel technology for the future. If you think about having some sort of selective catalytic reductor on a diesel engine, you've then got to carry urea. You've got to carry some reagent with you in the ship. Does the ship then have to replenish at sea that reagent? That would be difficult. We've spoken a lot today in the conference regarding unmanned surface vehicles and similar such vessels. Why would they have a constraint upon the power and propulsion system? Because often they are launched by a stern ram, which means you then have to look at exactly where your shafts, the shaft distance apart, where are you going to get the steering gear, how does it go in? This has to be designed into the power and propulsion system at a very early stage. Power density is something I've also mentioned earlier, and I really stress again, ships are expensive, bigger ships are more expensive, try to keep them small, try to keep the mission systems, the weapon systems that everybody's been discussing here, maximise the amount of weapon systems that a warship can carry, because that's what it's there for, means minimising the power and propulsion system, keeping the density of that system as high as possible. This is exactly what I'm saying in this particular slide. We need more flexible propulsion systems, and we need more flexible propulsion systems, and we need the systems itself to be more power dense. We're seeing globally, and it's not always the case, but I'm talking generically, fewer warships, but more multi-role, more complexity, heavier and larger mission systems. Greater focus on operational flexibility, and platform efficiency is very important. Fuel is a strategic resource. If you use your fuel to get to the task, you have less time on task. So the propulsion systems, we are seeing a huge growth in the electrical load requirements of a ship, of a warship, especially when you think of modern radars. They do take more power, phased array radars, etc. And looking to the future, perhaps electromagnetic catapults to launch UAVs, railguns are being, in some countries, being introduced. These sorts of type of weapons will put a huge additional load on the power and propulsion system, such that the power and propulsion system will be fully integrated with the weapon or the mission systems. And indeed, we're already looking at studies of having large gas turbine alternators propelling ships, but then while you're propelling the ship, how many rounds can you fire from a railgun, requiring so many tens of megajoules per gun? So the way we're seeing it is, we're seeing less mechanical propulsion, but fewer higher powered gas turbines in the sort of frigate destroyer area. If we look at a generic picture of power against, displacement, the size of the ship versus the propulsion power that's installed, these lines on this particular, these lines are constant speed, essentially, constant speed line, and going up on the chart, you're going faster and faster. Now these lines aren't on this particular, the boxes drawn here aren't hard lines, they're just an area, if you like, showing where things actually sit today. So if you had right down in the bottom left, you have an all-diesel, fairly small ship, still being able to achieve reasonable speeds. Electric propulsion, which we're seeing around the world from the United States Navy, the UK Navy are going towards more full electric ships, where the ships are propelled electrically. Actually, with today's technology, you need to put that into very big ships that don't go very fast. It's because the motors and the converters and everything else is quite big. And as you look at the top right of this sort of slide, you'll see the big ships going fast, US Navy, mostly gas turbine. But the system we think that is very interesting and should be looked at more and more in this type of vessel, these sort of escorts, frigates and destroyers, is a hybrid, where we use electric propulsion for cruise, but then mechanical propulsion for full power. If we go back a step, and I think this morning we were talking about the old Kodag type arrangements where you tended to have twin shafts, two cruise engines, probably diesels, possibly gas turbines, and then two big boost gas turbines. At the same era, on the left-hand side, the aeroplane world was flying across the Atlantic with 4 engines on the planes, because that's all they were allowed to do. You see 2 on each wing. We move to today's systems in frigates and destroyers. Increasingly, we're seeing electric propulsion, a hybrid system, electric propulsion for cruise with a single big gas turbine for full power. This is a system being adopted by many navies, as you can see on the right. You recognise the ships. And at the same time, the aircraft industry has gone from 2 engines per wing to 1. The reliability of the gas turbine has gone up considerably. So this is, if you like, a propulsion system that we have been offering, and indeed is going to be adopted in the Type 26 frigate and the new Korean frigates as well, fast frigates, very similar system. A single large gas turbine. It is capable up to 40 megawatts, driving into a splitter gearbox, but for most of the time that's not used. We design the electrical system, just the motors and the shaft, really to propel the ship up to about 18-19 knots without having to use the gas turbine. So in effect, the diesel generators become the main engines of the ship. because they're used for much more. It gives you a very good ASW performance. It's affordable. We've only got one gas turbine, the same number of diesel generators we already had, so the number of prime movers is down. It's very flexible, and the future-proof part that I think you can see at the bottom of this slide, if I put more electric weapons on this ship later in its ship's life, I can use in times of action, I can use the gas turbine to propel the ship and all the electrical power from the diesel generators for the weapons. The one criticism people make, naval engineers make, of having a single gas turbine is it's then vulnerable. If you hit that gas turbine, you've lost main power. Well, actually, we've spent some time looking at this. I mean, this is the top picture here that you can see is a standard old CODOG, CODAG type arrangement. And if you lost the gearbox space, you probably lost propulsion. Whereas with a single gas turbine, you can lose any one of the spaces without losing propulsion at all. Yes, you may be reduced down to 18 knots if you only got the electrical system left, but you wouldn't lose it all like you would if you lost the gearbox in the old days. I mentioned that having a large gas turbine, Rolls-Royce's offering in this market is the MT-30, which is in the new US Navy's DDG 1000 Zumwalt class, in fact 4 Rolls-Royce gas turbine alternators, because this is an all-electric ship, 2 very large ones and 2 smaller ones. The littoral combat ship as a mechanical drive, driving that ship in excess of 40 knots actually. The Royal Navy's Queen Elizabeth class aircraft carrier, and I mentioned before the Korean Navy frigates and the next generation Royal Navy frigate. Both the Korean Navy and the Royal Navy system are the same, COD-LOG. In fact, they're very similar systems, except the Korean Navy's frigate is smaller, but goes a lot faster. I think we've also heard about life cycle costs. In fact, these days we talk about whole life costs. It's not just the acquisition cost or the life cycle costs, they come together. And how do you reduce that? And actually we do the studies for many different navies. What are the potential options for their power and propulsion system for their warships? And what we see is, yeah, they want to see life cycle costs up front, defined, and perhaps even through some sort of long-term support agreement, actually the risk of the cost going back onto the provider of the system, i.e. Rolls-Royce, rather than people saying life cycle cost is only 3 when in fact it's 10. Oops. Okay. So what in effect I'm saying is combatants, the power and propulsion system is more integrated with it, is becoming more and more integrated with the mission system, must be power dense and cost effective, and we must consider both the initial acquisition cost and the support costs, the life cycle costs. They're getting more complex, the warships are getting more complex, they're multifunction, and environmental legislation is affecting the design of the power and propulsion system. What we need them to be is flexible and future-proofed. We think hybrids are going to be adopted more and more by navies for sort of 6,000-ton frigates, fewer, more powerful gas turbines, and power density. Frigates and destroyers are not the only ship we address in the... Frigates and destroyers are not the only vessels we address in the naval business of Rolls-Royce. It's more or less we define as government-owned vessels. So we really design and provide lots of equipment and different systems to all these 4 sectors as we see in the naval market. Combatants, before I mentioned to you frigates and destroyers, now moving on to things like the auxiliaries and indeed OPVs, that sort of type of vessel. We take ship design, we've had a presentation on ship design earlier, but actually a lot of our ship designs come from other world, come from another part of the business. This looks very much like a naval auxiliary vessel, but in fact, if you look at the top right there, this is the award-winning environment ship design. Actually, in the merchant field, this ship is propelled by LNG, liquid natural gas. We don't use that in naval tankers, but the equipment Rolls-Royce supplies to that ship makes this platform an exceptionally efficient platform, and efficiency is cost. It's fuel and everything else. This particular design comes in 3 different sizes and has a very unique propulsion system, which is what I wanted to talk to you about. This is what we refer to as HSG, or hybrid shaft generation, including a ProMass system, which is an integrated rudder and propeller system, which I'll talk to you more about. On this particular system, you can see a diesel engine, probably a medium-speed engine, driving a gearbox through to the propeller. On the gearbox as well is an electrical machine. I call it a machine because it is both a motor and a generator, and can be used as such in different configurations, which I'll show you in a moment. Looking at the ProMass down art, as I mentioned before, we integrated the rudder with the propeller itself, such that we maximise the efficiency of the back end of the ship. ProMass, as you can see, gives us reduced drag, less cavitating vortexes, etc., and reduced noise. The rudder itself is actually twisted because it sees a different flow regime above the propeller and below it. Obviously, the water flow across it is different, so that rudder is designed around what it's actually seeing. Again, reducing cavitation and noise and improving the efficiency. We've also adopted the propeller design to actually meet exactly what it's seeing behind that water flow itself. Coming back to the hybrid shaft generation system, this is a system we have proposed for auxiliaries, also for OPVs, corvettes, in fact, quite a few ships, but it's a variation on a hybrid, a standard just electrical propulsion system for crews. If we take this as a two medium-speed diesel engines, as I mentioned to you before, supported by 3 diesel generators, this particular system gives us great flexibility, and we'll explain why. If we're going to manoeuvre out of harbour, or if we're in some sort of close waters, we can use both of our diesels in exactly a traditional sense, driving through the gearbox with the electrical load for the ship provided by the diesel generators. If I need to go then on passage, on a slow passage, or for a long endurance, I can use these electrical machines as motors, driven by the diesel generators, providing power by the diesel generators to these as motors, and achieve maybe, if you size them correctly, we normally look at about 12, 14 knots on the electric propulsion itself. Quite obvious. This is a bit more clever. If we're in a peacetime transit, where there is no threat, we can run one medium-speed engine, use the electrical machine on that shaft as a generator, and provide power for the whole ship, and power the other shaft as a motor, using the other machine as a motor, so that we take away all the trailing losses of the second shaft. That makes that you're running the entire ship then on one medium-speed engine. The cost savings and the engine savings in hours, maintenance, etc., are quite phenomenal. Thank you. I need to finish. So that was the assisted trailing mode, running one medium-speed engine and supplying power for the whole ship. You have no trailing losses because we powered the other shaft using the electrical machine as a motor. And of course, when I want to go fast, I can use the diesel engines and the motors together in a cod-lad configuration to give me top speed. But by using cod-lad, it means I can put a smaller diesel in to meet the requirement that the Navy require. Whatever the top speed is, I can now put a slightly smaller diesel in. So in conclusion, sorry it was a very quick scamper through because I only had a few minutes here. Increasingly, the naval sector is seeing increasingly complex ships. And indeed the power and propulsion systems, the ship systems, the platform systems, and the mission systems are getting more and more integrated. We have to recognise that. I mean, as far as ship systems are concerned, the power and propulsion system has to run on the first day the ship is in service. And it has to run until the last day the ship is in service. It's the only platform system that does. You have to spend time looking at analysing the options in front of you and recognise, for example, where it's worth spending a bit more in initial acquisition costs to save a huge cost downstream as life cycle costs or reducing the whole life cost. We're seeing a lot more synergies. That system I showed you, hybrid shaft generation, is not yet at sea in a naval ship, but it's all over the offshore world, use it a lot. And we've done some numbers on ships that we've changed that had a traditional propulsion system in the offshore, changed to hybrid shaft generation. The fuel saving was phenomenal. We need to look at how we get the availability of naval vessels up. Again, we can use some of the offshore techniques. And we are looking at increasing the use of COTS equipment where appropriate in naval vessels. So when we had the presentation earlier, the design that Paul showed earlier of the Chapel is a COTS vessel. The Meerschaich is an out-and-out warship. The Meerschaich is designed against different standards, totally different class society rules, and is a warship. So there are two different types of vessels there. I'll be happy to take any questions. I think I'll leave it there. Thank you.